I'm starting the live stream. There we go. Let's do this. Ooh. I'm starting the live stream. There we go. Hello, Maths2222222. Welcome to Twitch chat. Welcome to Chapter 3, Symmetries of the Fairy Diagram. I've been trying to rush to get to this point. Hello, Mary. How are you doing? Because I think this is going to have content in that is completely new to me. I don't know what they're going to tell me about the fairy diagram at this point. All the continued fraction stuff, I guess, was like the reason that I'm in this book, because someone told me to go and look at the book for continued fraction reasons. But now maybe I get to use some symmetry theory stuff. Hello, Herb. How are you doing? Maths222 has worked out why the number of circles was increasing. I guess you mean in the forward circles diagram that we had last time. And there were two effects going on. There was like a slow increase over time, whereas you seemed to think it was drawing more and more. And there was maybe a kind of fast scaling, depending on how we had a threshold in there somewhere for like the maximum denominator we were rendering. And my intuition was that we should filter it on square root or something, square root of the length, because of how big the circles were. And probably now Maths222 is going to tell me that the number of circles was going up for a completely different reason. So we'll find out about that. Good. I think I've got my microphone working. Well, yeah, pretty sure. No, I am, because Marius responded to something I said. Good. Right. I'm going to try and... Oh, it's loading stuff outside the range. Ew. I quite liked it loading stuff outside there. Oh, I like a little bit of loading stuff outside the range, because I hadn't been clever enough to think about the problem that the contact points of the circle might not be in view. If it's loading lots of stuff outside the range, then I agree that gets problematic. If it's drawing loads of things, then if it's drawing circles you can't see at all, then I guess you can work that out for each value of Q. You know where the top corners of the screen are, or possibly you know where the edge of the screen is, so you can do some maths to work out for a particular value of Q, how much further do you have to look, or you could, I guess, not think and just check whether it ends up above. But then you end up drawing some massive ones that are above, but super high. So maybe you do two sorts of, I don't know. There's probably clever ways to cut out which circles so that you get the effect I want is just like a bit of a circle in the corner up there or something, which is quite hard to decide that you need to render, because the contact point for that circle is way over there somewhere. So the actual fraction for where it hits the x-axis, the thing we've been using to index those circles, kind of miles away. I'm talking about a very particular diagram. Maybe I should get it on screen. How much of this are we doing? Not certain. It's this one that we had last week, right? With lots of circles, where what we would like is to be able to zoom in. I can't remember how to do this. Oh no, to zoom in on a particular point. To zoom in, this one. To zoom in and to get it to render more circles on the way in, so that as you go, you see it's popping in circles on the way in, but without getting so many circles the Desmos breaks. And you've got a new version. Cool. Let's just load that one. Good collaboration in the sense that Maths222 is doing all of the work. That's a lot of circles. Okay, so I think thing that you're claiming to have fixed is that, oh, you've got the half in there. That's good. I like that. But this list of circles might not get large too fast. So it's drawing 78 at the moment. Something they've added to Desmos in the last week is this behavior where your list, it shows you the elements. You can inspect the list live, which is quite good. So now zooming in. Oh, I've done that thing where I don't center it. Let's try and center on that start point that you've put at root 2 minus 1. Yeah, so it's kind of controlled. It's staying at about 80. That's nice. I like it. Okay, good. Are you doing clever things on the range inside here? Ooh, yeah, okay, that looks cleverer than it was before, right? Yeah, you're adding on Is that the radius? Yeah, I gave them stupid names, didn't I? F and G. Okay, adding on a bit of radius to check whether that's enough. No, what's the square bracket doing? I'm not passing this square bracket, right? Am I? What's this square bracket doing? That's 2, 2, 2, 2, 2, 2. It's kind of, it's got some, I can see inequalities. I can see if it checks. Why has it got square brackets? Is it just supposed to be a real that's a real number that's multiplying this? It's like 0 or 1? Possibly. Doesn't really matter. Oh, it itself is. All of these things are lists. Maybe it is a good idea to wrap it in square brackets. Yes, it's this such that these things are true. Yeah, fair enough. There's no commas in there, right? I'm not going mad. Square brackets. Okay, fine. Whatever. Good. Okay. Yep, looks good. I love it. Especially love the rainbow behaviour, where sometimes, we've talked about this a little bit, sometimes the rainbow lines up and you can see bits of rainbow, sometimes it's going through the rainbow much faster as you cut through those fractions. Have we talked about that? That's something to do with how the denominator is increasing on the way through those tangent circles, which is the continued fraction rule kind of thing. You're doing the median each time or something. What are you doing? So you do the median, which means adding on. The relationship is something like you're adding on the denominator of this fraction each time, which might not be 1. Yeah, I'm just surprised you need to put square brackets around the condition there. Thank you. I'll just demonstrate. Doing what you tell me. Sometimes it's Math222 stream and I'm just typing. So, oh, no, you do want all of those, don't you? Because you're making a point. Oh, it's indexing. It's square brackets to select from that array. So, select from the array of the A array. Right, good. Huh, cool. So this thing looks like a function, returns an array, so the square brackets are accessing that array. That is weird. Because if you just look at it, you'd guess that the square brackets were the array and that that's a real number multiplying the array, but it's kind of nothing like that at all. Good. I'm going to make one change, which is just that I feel on my monitor I can see some little bits of light and I would quite like to not see them, so I'm going to change that to 20 just to push it a little bit more. There we go. Good. Okay, thank you. I don't know what version we're up to, so I'm going to put 5. Thank you very much. Oh, and I should close that because it annoys my computer to be running Desmos in the background. Maybe not that one. Good. Okay. Was it 5? It's 5 now. Right, okay. Back in. Oh, by the way, I have a book recommendation before we move on. Maybe everyone else is already aware of this book. I found out about it last week. It's Evan Chen's Napkin. I don't know if people have seen this before. The concept here is it's loads and loads of pure maths described properly, but without the proofs. So just giving you the gist of lots and lots of pure maths. The PDF is 1,000 pages long. I don't have time to read all of it, I think, in my life. But I've enjoyed flipping through it and getting a kind of sense of bits and pieces of maths. Their point up here is that most of the maths you see at high school is either just someone telling you Harry Ball theorem lol, or doing loads and loads of hard work. I'm gonna read it this year. It's 1,000 pages, Mary. You know, in the Hatcher book, we are on page 70, and we have dedicated what, 2 months? So 20 months. Yeah, that's not too bad, is it? Actually, that says we can do it. Maybe that's not too bad. Maybe that's just like studying for 2 or 3 years. Anyway, I've enjoyed flipping through it. It's got a map at the front, which is the sign of a good book. Love a book with a map. And for me at the moment, it's been a good way to quickly skim through differential geometry, which I know nothing about differential geometry, but skimming through it gives me the kind of impression that the thing it reminds me of is hanging out with people I was friends with who did do differential geometry, who were trying to explain to me over lunch, like the gist of what's going on. So it reminds me of kind of lunchtime, hanging out with people who know what's going on and who might explain it to me. So that's what I quite like. It's really hard and would take, forever or conservatively 5 years. I'm just putting it on the screen because if you're in the position of wanting to find out lots of hard maths, doing it properly, but also just getting a gist of what's there to kind of motivate yourself to go and study the proofs or go and do it properly, then this book's got like 1,000 pages of that. And does linear algebra, I think, properly. I'm not certain that I learned linear algebra properly. This person did. They are very, very keen on linear maps being the way to understand things. Oh, little battery indicators come on there. Have you seen that? Let's fix that. One of these. It's not a live stream without some USB devices. Which is why we currently have, how many? 1, 2, 3, 4. Yeah, several USB things. Let's make that go away. Oh, sorry for the Windows noise. I don't know if I broadcasted that. Did I broadcast that Windows noise? Maybe. Yeah, no, 10%. 10%. Also, how well we're doing at reading this book. 10%. My energy levels on a Sunday afternoon. 10%. That's the chill maths way. Who do you think's at 10% around here? Yeah. Anyway, so I'm enjoying flipping through the napkin book at the moment. It is, in places, extraordinarily difficult, I think. It has loads of really, really hard problems. And if you just skim down to like 700 pages in, then I have no idea what any of this is. So it's quite exciting, in the sense that, just read this simple 1,000-page book and you'll be all right. I'm joking, of course, like the book is 1,000 pages, but you're supposed to follow a particular route. So for me, the bit to read is sort of linear algebra and topology, and then I'll understand maybe some differential geometry. And I'm skipping, if you can see in tiny writing, is skipping from chapter 18, skip to chapter 43, like a find your own book. Yeah, it's got homology in, right? It's got homology in. Yeah, that's the thing I've got to learn. I've realised I'd like to actually know what's going on with Stokes' theorem. This is quite embarrassing to say because I'm teaching a first year course where we do sort of easy stuff with Stokes' theorem, and I thought it would up my act if I could. It'd be an improvement to my performance there if I could also allude to some kind of cohomology fact, which you don't need in order to do the course. It'd be good for the stronger students if I could say something vaguely coherent about cohomology. Yeah, look, there you go. Huns and bun. Oh, that seems fine, right? Good. You did hear my Windows noise, even though I haven't got that bit switched. I think you're hearing it over my microphone, and I've got something very weird going on. That's how you get the stream. How you get the stream alerts, right? If somebody subscribes or follows, I think they travel through the air in this room rather than through my computer, which is the mad way of doing it because it's an unprofessional live stream. Which reminds me, I have gained a follower. We're doing it. Slow progress on this one as well. I'm being followed by mad people. Their username. So mad people are following me, which is a pretty scary notification to get midweek. But there you go. Yes. That was the yes. Right, good. Got it. Right. I think it is time to do some symmetries to the fairy diagram. I've looked at this. There's about 18 pages of symmetries. I'm not sure what to expect, but I think because I can see circles, we've talked a lot about circles, and the upper half plane, that rings a bell for me. I think we're possibly going to talk about Mobius maps, which are maps of the complex plane like this. I could be completely wrong, but I think we're probably going to see some of these, because these send, the result is that this sends circles or lines to circles or lines. It kind of mixes those concepts together. A straight line is just like a really big circle, and this map kind of mixes those two things together. Okay, in particular, I think they're going to tell us about, I can see over here some circles that are being sort of transformed around, and I worry that we might be about to try and do all of the symmetries of the unit disk, which is quite hard, I think. But maybe in 18 pages time that'll happen. Who knows, maybe there's none of this, and it's all just continued fractions, which the previous 2 chapters have been about. So maybe it's just that again. But it's nice to try and guess what's going on. Right, okay, so what are they actually telling me? For the upper half plane, it's a fairy diagram, there are symmetries which translate as well as reflections. This is good for me so far because those are both examples of this with no denominator. So C is 0, D is 1, gives you nice transformations like translations and scalings and reflections. Could also be drawn to have a 120-degree rotational symmetry. That is not obvious, right? So we had this thing before where you put the fractions around the outside and you join them up based on some rules. It is not obvious to me that you could distort it like this. What are these 3 numbers? It's completely different, right? Or maybe these 2 are the diameter ones? And then because it's sort of nested, right? So maybe I take this line, so A and B, maybe that becomes this, still question mark, B over here, this line, and then everything in between. There's a kind of repeated process here for the fairy diagram on the left. You can think of that as being a line across the middle and then connect the midpoint of each bit of the circle using bit arcs of circles that are orthogonal to the unit circle sometimes. So you do that around the top, and then that creates smaller regions. Then you put the same sort of decoration in there, and then same joining the midpoint each time. I guess you could do that if that's A and B over here. Then this would be the sort of midpoint of A and B on one side, and that'd be the midpoint of A and B on the other side, and you can build it like that. And if you put A and B just in the right place, it gives the impression of a equilateral triangle. You started this off. Okay. These are supposed to be the medians in some way, and now I'm realising that I can't remember the difference between the top one and the bottom one. I think it is just negative numbers. Oh well, we will get there. Okay. Our purpose in this chapter is to study all possible symmetries. Broader sense than the familiar meaning from Euclidean geometry. It sounds. You see, that sounds like someone setting up a broader sense than familiar from Euclidean geometry. It sounds like someone's setting up a larger class of transformations, right? Was the top negative? The top was negative. I don't think it matters. I think you could define either. In my memory, about 1 million pages ago, the top was negative. The top was positive, sorry, but here's a link. Let's have a quick look. No, let's not. Either works. Thank you. Good. Right. Right. Okay. We're going to find formulas for all of the symmetries. Oh, I skipped a bit. Invertible transformations that take vertices to vertices, edges to edges, and triangles to triangles. That is going to be Mobius maps. I'm now getting confident because they're talking about taking circles to circles. Similar algebras, simple algebraic formulas. Yeah, this is somebody trying to set up Mobius maps. I hope. If not, I'm going to be very surprised. Here we go. Our first goal to find formulas. Find symmetry transform. Okay, find formulas for all of them. Good. Specify where each vertex is sent, so have a form. Transforming x over y, I want to see this fraction x prime over y prime. Reflection of the circular fairy diagram across the vertical axis is times fractions upside down. I do want to go and look at that picture of fairy diagram now, don't I? Because they're now talking about obvious transformations. It was somewhere back here. No, that's way too early. A little bit further on. Start of chapter 1. That's what I want to find. Still in the preview. The preview sets up chapter 6 being a cool bit. It does some stuff in 3D that we skipped. Chapter 0. Fairy diagram with, on this page, positive numbers upstairs, negative numbers downstairs, and the fractions the other way up on the right. So they're talking about this reflection of the diagram corresponding to, what does it do to the fractions? 2 over 1, 1 over 2. How was this built? So this is built on medians. So adding the numerators and the denominators separately. So 2, 1. So how did this happen? I guess 1 over 0 and 0 over 1 are the other way up. We have 1 over 0 in this diagram. Don't worry about it. They're really just vectors. They're disguised as fractions, but they're really just... never mind. Writing them as fractions introduces all sorts of... Anyway, never mind. Oh, I've doodled on this one. I've broken the symmetry. I don't love that. Let's clean that up a bit. Okay. Is it obvious why it was the other way up? Well, okay, from this point, it's true, and then by induction, you have things that are the other way up. You do the median rule, which just means adding numerators and denominators, and they stay the other way up, because you're just doing the same sums upstairs or downstairs, other way up on the other side. So on this side, the thing you're doing, the very first thing is adding 1 to the numerator over here, whereas over here, this arc, putting in the midpoint and labelling it, you use the median rule and it says add 0 to the numerator, add 1 to the denominator. We have this median property in this book, where we take 2 fractions and just add their numerators and add their denominators, and call that the mediant, and this is really not how you add fractions. It is how you add vectors, but we're writing them as fractions. Okay. Have they done anything about fractions? I mean, the fact that they are continued fractions for the fraction is relevant, I suppose. Like, the value of the fraction is important, but for a lot of the book I feel like we're actually dealing with vectors. Never mind. Right, I need to get back to page 78-ish. I think I've overshot it by hitting there. Way overshot, that's 140. That was very ambitious. Somewhere around here. Matrices, spoilers. Maps, spoilers. Okay, so we're down here. So we have reflection. Across the horizontal axis is negative, backwards and forwards. Yeah, you can do a 180 transformation by doing both. There you go, minus y over x. For the upper half plane, it's this. Leftward is that. With the exception of x over y plus minus n. They're preferable. I don't know what's going on there. Okay, I'm skipping ahead. Yeah, we're going to do a lot of stuff in this book. If we keep going, there's a lot of kind of quadratic forms, primes of particular formats. And hopefully the symmetry stuff is related, because I'm going to try and throw 2 hours of my life into learning the symmetries of the fairy diagram, and I'll be disappointed if that's not going anywhere. Right, here we are. There it is. I was only 1 page ahead, but we got there in the end. So just by having these translations, inversion, and scaling. Where's the scaling coming from? I thought translations and inversions. Yeah, so translations and inversions almost get you there. You do want scalings in there as well to generate these maps. Oh well. And we're going to call them linear fractional transformations today, not Mobius maps, but we'll leave that notation for you. Yeah, the disaster case is that we get to the end and then it says you have to go and read those number theory notes again. I read some number theory notes last year and they were really hard. They were by Vicky Neal, so they were great fun, but also really hard. Good. Okay, we've got these AZ plus B over CZ plus D. What did I tell you? Aha! Brilliant stuff. Are we now going to prove things like, at one point in my life I did learn lots of facts about Mobius maps, and we're going to learn them all again now. Here we go. Fractions x over y, including plus or minus 1 over 0. What are you doing here? Correspond to pairs. Yeah, correspond to linear transformations. That is fair enough. Yep, I've seen a matrix before. They do things like this. They give symmetries to vertices to vertices and edges to edges. Right, is this now where we get some nice restrictions, like possibly AD minus BC being equal to 1? It's always AD minus BC. Plus or minus 1. Let's get plus or minus 1. Because, well, the labels aren't actually the labels are fractions, but they're not actually the value of anything at that point, are they? Oh, but they... No, because this is not the image of the unit circle under... This is not the image of the real line under projection onto the circle. So I don't know what's going on. right? Okay, vertices are labelled fractions P over Q in lowest terms, with P over Q determining the same value vertex as this, but that's all right, because if you give me minus x and minus y in your fraction, then everything's okay. For t to take vertices to vertices means that you have rational numbers. For a fraction P over Q in lowest terms, we would like this to be in lowest terms. I mean, if you give me a fraction with whole numbers in, then you're definitely going to get something rational out, so I'm happy with that, I suppose. And we're talking about the behaviour of the numbers written on... This is really strange. We're talking about the behaviour of the numbers written on the points. I was thinking about the behaviour of the positions, or the points in the complex plane, with my AZ plus B over CZ plus D, and now I think I'm being told that you can just do those operations to the labels. I'm a bit uneasy about the relationship between the labels and the actual positions that they're at, because we just put them in the midpoints. So now this is just going to be like number theory, right? Here we go. In matrix terms, this last condition is saying that if this thing has determinant plus or minus 1, we want this to be an edge also, which means check the determinant of this, which means that this should have determinant plus or minus 1. Yeah, determinant is multiplicative, so here we want this thing to have determinant plus or minus 1. The exact condition we need is that AD minus BC should be plus or minus 1, like it always is. Called it. Right, good. Welcome back to the show. This is Chill Maths, where we try and guess what's going on in a textbook that we're reading. And it's easy, because the answer is always determinant plus or minus 1. The special linear group. Special linear, am I saying that right? Special linear group. Yeah, probably. Look, I'm happy. I'm just going to leave it. Okay, here's a proposition. If the matrix with integer entries is determinant plus or minus 1, then the associated linear fractional transformation, which takes a fraction and returns this fraction, takes vertices in the very diagram to vertices in the diagram, and takes each pair of vertices that are joined by an edge to another pair of vertices that are joined by an edge. What do I think is going on, really? Because that does correspond to a transformation of the unit circle, but that's not really what's happening, because the fraction on the label doesn't actually tell you where the point is. It's related. Anyway, it's going to take triangles to triangles. It's kind of like an abstract thing that it's just taking... You could say that it was acting on the real line, I think. There's no kind of sense of position at all, just this thing remixes Q. It's just a map from Q to Q. That's the best thing to say. It's not a map from C to C, it's just a map from Q to Q. Which is a bit disappointing, because I think there is a map from C to C that does the same thing. Because it's the same map, probably. But why are we doing this on Q? Oh, we only care about rational numbers in this book. And I think, yeah, if you're talking about complex maps, then dealing with the rational points is probably good enough, isn't it? Right, okay. Fair enough. I've been browbeaten down to real numbers. So excited to have complex numbers in here, but no, I think we've been beaten down to just having a map from Q to Q. Yeah. Okay. Triangles go to triangles. Oh gosh, yeah, okay. Yeah, that's all right. T takes vertices to vertices. What is this proof telling me? Yeah. What about square root 2? Yeah, I know. Because we had all those continued fractions of irrational numbers. I think this is going to say something like, ooh, root 2 isn't really on the fairy diagram, but it's pretty nearby to, you know, where should it belong? Ooh, nearby to all of its convergence. And the convergence are rational, and they're transforming like this, so they've all gone over there. So root 2 has gone over there or something. This is a bit disappointing. So yeah, I do think you should just. I mean, it really has gone to this position just by raw continuity. I think the root 2 should go over there because 1.4 is going somewhere over there, and 1.41 is going somewhere over there. Oh, that'd be a good moment to bust out some convergence to root 2 if I can remember any. 7 over 5. 17 over 12. I can remember some. Brilliant. 29 over 41 over 29. Good, right. Ha! Can I remember numbers? Something I can do. Right, not very chill though, is it? Me barking numbers into the ether. We're going to use the notation LFZ. Are we? I don't like that. What are they? What are we calling them? Linear fractional transformations. We're going to call them LFZ. LFZ. Don't love it. I guess that they're built of integers. They're linear. Yeah, fractions. They use integers. Yeah, fair enough. Okay. Yeah. I think that's what I want maths to do. There's a function that gets them all in the right order. Not literally with the median in the middle of the places, but if you just project the real line onto the unit circle, then you're almost there. You get the kind of important stuff that we want about the... Well, what do we want? I was going to say about lines not crossing and... Yeah. So thank you, Home Biscuit. I'm going to go French for that one. Home Biscuit, thank you for the follow. Thank you for testing out my follow system live on stream. Yeah. What do I think? I think in my head it's going to be a slightly deformed fairy circle that I'm really working with. The book's called Topology of Numbers, so let's evoke a tiny bit of topology, or that kind of topology flavoured sort of thing where I say the exact positions don't matter. Maybe my mental model is that the real number line actually exists. That thing is the thing that you know and love. The distance between 1 and 1/2 is 1/2, stuff like that. And then project it onto the unit circle using the projection map. Can I remember what that is? No. Can I work it out? Yes. So quick side doodle over here in the margin or something for the fair projection map. How far left can I draw? Perfect. So the real number line I kind of believe in. That's where I think the fractions actually live. And then the kind of concept for the fairy diagram is that you put all of these things onto the circle. I'm going to get this picture rotated around, I think. Yeah, mine's going to have 1 over 0 in the north. Yeah, stereographic projection map. Stereographic projection map. No. And this is going to get all the points in the correct order, I think. Yeah, the median is between the two numbers. So as long as I get it somewhere in between, then iteratively on the way down, I'll be placing my median somewhere in between, just because, yeah, they're somewhere. So you can do this stereographic projection. It's mentioned in the book quite early on, but they say that it's a kind of deformed version of the fairy diagram where the median is not literally placed in the middle of the arc around the circle. Let's work out the map, because it's going to be a Mobius map, or what we're calling today a map from LFZ. So if I have a point, P over here, I would quite like to find the point on the unit circle, such that the line, what is this line? This is 1 on the y-axis. So I'd quite like the line 1 minus x over p, because that's the straight line that goes through When x is 0, y is 1, and when x is p, this gives 0. And I'd like x squared plus y squared to be 1 to find this point on the unit circle. And this is not as hard as it looks. I mean, it doesn't look that hard, I suppose, but it's not as hard as it looks because we know that one solution of this quadratic is going to be the number 0. Because, behold, here is that very solution where x is 0 and we're up there. So I just need to work out the coefficients, which is not too bad. Maybe I don't even need to work out the coefficients. The 1 cancels on both sides is what I'm saying, I suppose. Yeah, I've seen this formula before because this is the Pythagorean triple sort of thing, isn't it? So this is p squared minus 1. Here's where I now sort of beans it up just to apply beans just to prove that it's difficult, right? That's an important trick. I have to make sure that I make a meal of it. So x is 0 or x is 2p over. Really having a hard time over here. P squared minus 1? Doesn't look right because when p is 1 that's going to infinity. What have I screwed up? Yeah, p squared plus 1 probably. Yeah, minus sign erroneous over here. Adding a square. So when p is 1, this goes to 2 over 2, which is 0.1, which is what I expected. When p gets very large, this gets very close to 0. When p is negative, this gives a negative number somewhere down here. Oh, no, when p is not true. No, yeah, when p is negative, it gives a negative point on the left somewhere. So for me, this is going to be a fairy diagram where I get 1 over 0 over here. I have 1 over 1 over here. I have minus 1 over 1 turns up on the unit circle exactly here. The point of intersection is the point itself. Over here I have the image of 0 over 1. When p is 0, you get x is 0, but that's the other root. It becomes this kind of repeater's root. And in fact, in that case, my diagram is not very good. So maybe I should put unless p equals 0, and I should think about the 0 case differently. But there we go. So this is then going to map 1/2 to somewhere in between. So this is like a label. It's not the number 1/2, it's the label that goes on that point of the fairy diagram. But it's somewhere in between. It's not at 1/2. So if you find the image of the real number, it's 1/2. You find 1 over, what's this going to be then? I can't add. 5/4. Oh, not bad. 4/5, which corresponds to the Pythagorean triple 3, 4, 5. Because the y coordinate is 3/5. Yeah, good. What's that got to do with anything? Well, let's write down the y coordinate then. The y coordinate at that point, if you follow this through, so divide, subtract 2, 1 over 1 minus this, or if you prefer, write down the thing which, when added to the square here, will give the right number. And I believe it's p squared minus 1 over p squared minus 1 over p squared plus 1, sort of Pythagoras stuff. Now I said this had something to do with the linear maps, and I've got all these p squareds. So what's going on? Am I just wrong? Maybe I'm just wrong. Wouldn't be the first time. Let's think about this. It should be right. Sending a line to a circle. I should be able to do that with the Mobius map. But maybe this isn't the Mobius map. Maybe this is some random map. Deep thought. Nah, seems fine to me. That's not it. It's projection, not a Mobius. It's stereographic projection, not a linear map. Doesn't look linear, does it? It's got all this divided by p squared plus 1. So yeah, so we've set the real point p. So it's gone to 2p plus I p squared minus 1 over p squared plus 1. How do you square that circle? We don't square it, make it round. So how circles are supposed to be. Don't know. Can I find the Mobius map that does this and check that it's equal? Maybe the Mobius map would be different. Mobius maps are sharply triply transitive, so if I just make sure that I send 0 down here. Yeah, so let's do it again, but using a Mobius map. So is this non-linear? It looks weird, but maybe it's just an artifact of using real P, and that I should be thinking more generally. So let's see if we can find a Mobius map that sends 1 to 1, 0 to minus I, and minus 1 to minus 1, and has the form AZ plus B over CZ plus D for complex numbers. I think such a map exists. Let's find out. So what do these tell me? So that is A plus B over C plus D should be 1. Minus A plus B over minus C plus D should be minus 1. And B over D should be minus I. Collection of equations, isn't it? There's a scaling factor as well, so maybe I can afford to take this thing as well. AD minus BC is 1 because divide top and bottom by square root, so maybe plus or minus 1. Divide by the absolute value of divide by the square root of the absolute value of AD minus BC, upstairs and downstairs. I'm using real numbers. Let's find out. Right, mumbling about Mobius maps. I think there's a map of this shape, which would be nice because then it would match up with the things in the lecture notes here about mapping around the unit circle from one configuration to another. Let's find out. So if I solve all of these things, what will I get? A mess. No, right. Let's say, let's try D is 1, B is minus I, and then what have I got? I've got B is minus I. Okay, so then I've got A minus I over C plus, is equal to C plus 1, let's say. And I've got minus A plus I is equal to C minus 1, minus minus. Can I get all my minus signs right on stream? Let's find out. These are pretty good because I can add them. I can add them and I'll get C equals 0. Oh no, now I'm stressed. Maybe this is fine. And A is, oh my goodness, what is it, A? So just, why am I so bad at this today? I'm always bad at this though, aren't I? 1 plus I. So it gives a minus y, minus 1, cancel the I, and it's all good. I'm very stressed about this system of equations. So my map is 1 plus I, z, minus I, over, no z's down here, and d is 1. Oh, so it's a very simple map, isn't it? No, that can't be right. What does that send 0 to? Minus I. What does that send 1s to? 1 to. 1 goes to 1. What does that send minus 1 to? Minus 1 goes to minus 1, take away 2i. So I screwed up over here somewhere. This is fun. Oh yeah, there's a minus I over here. Minus I because b is negative I. That minus sign followed through. Can I get all my minus right? Can I get all my minus signs right on stream? No. Okay, this is useful for me. I'm not sure it's useful for anyone else, but thanks for hanging out. I've got a system of equations. I am struggling to solve them. I still think C is, no, do I think C is 0? Or do I think C is like minus I or something fun? So if I add these equations, then the A's cancel, and I get minus 2i on the left. Ooh, and I get 2c on the right. So I sort of think C might be minus I, and A can be 1. And then the A's match up, the C's match up. All looking good so far. So then I think we're sending Z to Z. Oh, it's going to be very simple in the end. Z minus I, Z plus 1. So setting d to be 1 was maybe a poor choice because I've got this minus I around here. Maybe I'll multiply top and bottom by I. Might have screwed that up, let's think. 0 goes to 1 over I, which is minus I. 1 goes to I plus 1 over I plus 1. Minus 1 goes to I minus 1 over I. No, 1 minus I over I minus 1, which is minus 1. I think we're good. So then what on earth is going on to compare this non-linear map up here for stereographic projection that sends the real line to the unit circle versus this map down here, which does the same thing, but mildly different? Oh, maybe not mildly different, right? If I rationalise the denominator down here, then I can get something that looks quadratic. So if z is real, then I can multiply top and bottom by z minus I to get z squared plus 1 downstairs. Factorising z squared plus 1 in complex numbers is fun. So multiply top and bottom by z minus I, and then upstairs I think I'll get exactly the right thing. Multiplied by z minus I. So I'll get upstairs iz squared, which corresponds to this thing here. Iz squared, I'll get a z term, and then another z term, because minus I times I is 1. That corresponds to the 2p over here. And I'll get at the end, or something like another z squared or something nice. Oh no, something like I. Let's just write it out. Stop messing around and write it out. Z, take away another end, 2z, and then minus I, z squared plus 1. So in particular, if you write it as p, then you have 2p and p squared minus 1 times I. It's exactly the same, so it all agrees. So that was the same map all along. Oh, good thing I checked. I've learnt that even if it looks like p squared plus 1 stuff, then this can be a nice simple map. Stereographic projection, I can now try and remember that it is just iz plus 1 over 1z plus I, which I'm going to write like this, in a little matrix format to help me remember it. I think I've got all my 1's and i's correct there, oh my goodness. Stereographic projection, 1i, I1, oh, that's not bad. I1, 1i, Mobius map, which has got determinant. Oh, that's irritating, it's got determinant. Yeah, that's not got a great determinant, has it? What's the determinant here? Minus 1, take away another one, minus 2. Maybe I should divide by 2. Maybe I should divide top and bottom by root 2. It works. I like it. I think it's fine. But the columns aren't normalized, and maybe I should normalize them. There's a factor of square root 2 hanging around because 1 plus I is not a unit vector unit in the complex plane. One mixed language. Desmos says it works. That's nice. So yeah, the way you would test this in Desmos is to throw random numbers in. Oh, can we do this? Hang on, don't tell me. But can you just switch on complex number mode and then it does it? Let's find out. So complex mode, which is rapidly becoming one of my favourite things. So I just want to see. So I want a kind of slider, right? A sort of parametric thing almost, where I have like iz plus 1. But the z, that should be some sort of real slider. Yeah, there we go. Good. iz plus 1, different values of z. I'm using t because Desmos has this kind of built-in thing that can recognize that as being a parametric parameter. Parametric parameters. The stupidest thing I've said in a while. Yeah, and where's that gone? I don't mean that, do I? Oh. The t should be over here. Yay, nice. Good. let's put particular points on as well to illustrate this. So for a particular real number a, then we get this kind of points around here, where as you change the value of a, making a very large, it gets very close to the North Pole. Making a negative, it goes around to the other side. So the correct label for that point at the top is infinity. And this sends kind of real points, like in this case, 2/5 gets sent to a point on the unit circle. Drill the line between the 3 points. Oh, what do you mean the line between the 3 points? Which line? Oh, I should draw in my line or something. Right, yeah, no, you're right, yeah. I should mark in this point, A0, and I should mark in the point 0, 1, and I should draw in the polygon, right? This one. The 3 points where we initially started this experiment. Can I just throw this, please? Can I just throw that? Oh, bother. This should be A0. Ah, bother, okay, fine. I will calculate the real elementary parts of this thing. Oh, you're going to make me wrap this in another round of brackets, aren't you? Desmos. There you go, that's the line. There's your line. But I can move A and I get this red point. And there you go, projection. That's actually quite fun. There you go. Oh, I should be writing these as complex numbers. Probably. For me, the number A is a very special sort of complex number where I'm putting this real number in. But you're right that if we had this as a kind of point, this was just A. It'd be nice to move it up and down. But then we're not projecting it anymore. Is there a way to visualize that? So, let's define the function. The Desmos complex numbers gives us new ways to visualize stuff, right? Which we should explore. So I think that works. And then this should just be f of t. Brilliant. Okay. So now we can apply f to other numbers. At the moment, I'm just applying it to real numbers. But what if I had this going on? Then what do I want? I want this to be the point AB. I'm kind of interested in not that point where it meets the unit circle, but I'm interested in, so the red point should be f of A plus BI, and that should be the thing that we put inside here as well, not just looking at the real component, but looking at this. Question, is this still a triangle or is it now a straight line? Triangle. So points, yeah, okay, kind of nice. This lets you map. I don't have map polygon right now. So this lets you explore where stuff gets mapped to around the inside. So as you go out to infinity in any direction, you get to points that are kind of near to that purple point, which is like the North Pole. More or less. Around here I'm not very far away. Crossing the circle is crossing the real line. And then the inside is kind of the inside. So asking where that lower half of the circle is the image of the upper half of the circle. Or is it the image of the... Yeah, no, it is. And then down here goes over there. So I'm moving the blue point and watching where the red point goes. It feels like being a cat following a laser pointer, right? Like, oh, that's very interesting. Where's it going? Why is it jumping around so much? Why is it so lively? Get it. I'm Imogen Rex. You got points for tea. Tea time. Oh, I'm excited. So far we have read 1.5 pages, then I got distracted by interpreting everything in terms of Mobius maps. The Mobius maps haven't exactly helped, except Well, they've given me a way to think about the projection from points on here to points on the circle using what I think we're calling, well, I'm calling it a Mobius map. And then off they go. Oh, can I put A plus IB into my polygon? I really thought I couldn't. That's unhappy. Do I have to format all of them like that? Maybe if I format all of them like that, I'll be happy. No, it's very unhappy with me. Goodbye. Okay. Good old Mobius maps. Maybe the thing that I remember the most from first year university maths. Good. Okay, what are we doing? Oh no. We've got, as far as thinking about these linear maps, which are going to map around rational numbers to rational numbers, and they kind of preserve the determinant fact that for Fairy was an idea about which semicircles you draw. You draw ones between fractions where AD minus BC is equal to 1 or minus 1. And that property follows through these transformations. So when you do one of these, you're fine. Okay, and they're all Mobius maps, but with real integer coefficients. Because we're only thinking about transforming the reals. If you have to send the reals to the reals, then your Mobius map has real coefficients. I am really struggling with the way that the circle lives in the unit, lives in the complex plane, but is labelled with rational numbers from the real line. It's not the real line, but we're thinking about this transformation in terms of what it does to those rational labels, rather than the complex number representing the location. I'm really struggling with that distinction today. That's been the main thing in, oh gosh, first hour, almost tea time. That's why Mean Machine Rex is here. Okay. There are inverse transformations because there are inverse matrices, I think, more or less. I hope that's how it works. If not, what are we doing? Yeah, fine, okay. Yeah, it's inverse matrix up here. And that works because we really are just doing matrix multiplication. So the inverse matrix of better get us back home again. And these are invertible because the determinant is non-zero. Good. Yeah, okay. We can get back again. Never send two edges to the same edge because it's invertible. Good, right. Can you bend the number line into a ring? That's what we're doing. Here it is. So if the largest number you know about is 10, then let me show you this. And let me switch off this. A is now real. And B should be 0. Okay. Here is the plan. Mean Machine Rex, just for you. If you give me any real number, then the red point is showing where I'm going to bend it to. And so the red line is kind of curved round. Of course, the real number line is very long, so I also need to compress it down. So as I get close to that purple dot, there's some compression going on. So even if I go out as far as 10, I'm only getting a little bit closer towards that purple dot. It's kind of unreachable using real numbers. The way I'm calculating that red dot is just that I'm drawing a straight line from blue to purple and crossing the unit circle somewhere. So I've got a kind of laser guided for where I'm going to bend the real number around to. Kind of natural thing to do is to send this middle bit underneath and back up again, because then you're still doing this kind of straight line fact. I should draw in the straight line. I've realised I can do that with the... there is no line command. I've realised I can do that with... no, I've got to type it out again. Good. This line. Oops. So as I drag this around, I get different points on the circle. This map is pretty straightforward using complex numbers. It's just you take your initial starting complex number in blue, and you multiply by I, add 1, divide by the number you was thinking of plus I. That's a whole there's a whole shape of functions like this with numbers in these 4 positions. They have some nice properties. Yeah, it's just stereographic projection, but it's one example of a kind of transformation of that shape with 4 numbers in, called a Mobius map. We're going to be interested in those because, well, if you did one of these if you did some weird transformation that shuffled around the real numbers first and then did this to draw them onto the unit circle, then you'd get perhaps another version of these fairy diagrams that we've been doing, where maybe you translate everything and then project it onto the unit circle using this. That would give you a different fairy diagram because things would be in different places, but topologically or something, you'd still have the same sort of semicircles going around. Because this map is very nice, it sends any semicircle that you draw, you send every point of that, you follow through this function, and you get a semicircle. That feels like something I should demonstrate. I can demonstrate it. It's going to take 30 seconds, isn't it? I know you've done tea time. Thank you, Mary, for doing tea time. I'm going to have 1 minute to draw a semicircle and then show you the image of the semicircle. Here we go. So G of t needs to be, I need a midpoint, and I need kind of exponential thing. So I need a radius, and I need this to go, yeah, okay, so I need to add these 2 numbers, and then I want t to go from 0 to pi, so then I can change where I put my semicircle, and I can change its radius. That looks like a good one. So this point at the end of the semicircle goes there, this point at the end of the semicircle goes there. Make it slightly larger, I think, and shift it slightly to the right. So this end point goes there, that end point goes up there, but I can calculate through, just using f, my function, all of the points in between. Right, from 0 to, and same range, pi. There it is. Yes, image of a semicircle. Complex mode in Desmos is so good. So there's the image of that circle. Every point on the semicircle gets mapped to an image, and you will notice that that is part of a circular arc. It's part of a circle where the places where it meets the red unit circle are orthogonal. They're at right angles to the red circle. If I zoom in, that's a right angle, baby, because the Mobius map preserves right angles. So in theory, I could take something like, in previous Desmos sessions, we've made a whole list of midpoints and radii for semicircles that we're interested in, and I could take those from the upper half plane model that we've been drawing in Desmos, and just sending them through this function f, which is pretty straightforward definition, just sending them through that function, I could draw them onto the unit circle, and the upper half plane gets mapped to, why have I started that sentence? The upper half plane gets mapped to the inside of the circle. So that's why we have these 2 sorts of fairy diagram that we use, because you can just use this map to transform them together. So I am going to think about these as Mobius maps after the break, I think, because although the shuffling around of the real numbers using integer matrices of form AD minus BC is cool, I then want to cast them all onto the unit circle using this one last Mobius map. So if I'm allowed to use Mobius maps, then I can do the stereographic projection step as well. And then I suppose my symmetries of the circle are something like, if you want a symmetry of the circle, perhaps we transform it to the real line using the inverse of this function, transform it to the real line, and then play along with whatever the book says about transformations of the reals, and then send it back again. And there's a sort of slight awkwardness that in the book they sometimes draw this picture where the midpoint of the mediant is drawn geometrically. So this kind of fairy diagram in the book is drawn sometimes with the medians like right in the middle, and mine doesn't do that because stereographic projection doesn't do that, but it also doesn't really need to do that. So kind of like this point for me, which is the number 1/2, I would draw it at the image of 1/2, which is a slightly deformed sort of thing. Let's do that one really quickly. So this is the semicircle that goes from 1/2 to 1. So it's got radius 0.25, radius 0.25, and it lives at 0.75. It's that one. So it goes down to here for me, which is not the point. I say yeah, which is not the point in the middle geometrically of that quarter circle. Let's put the other one in just for fun. Can I do a list of these? I bet I can. Desmos is good at lists. So let's do another one of radius 0.25 at 0.25. There you go. So in the upper half plane model of the fairy diagram thing, we might have curves like this. But for me, the image of these things, because I'm mapping 1/2 down here, these green curves are not the same size as each other, but that doesn't really matter. Everything is kind of just continuing like normal. And we should put in here, just for completeness, I think, the big arc of radius 0.5. So the kind of top one, because we're really interested in these triangles. So black showing you in the upper half plane where stuff is, and then green showing you the kind of distorted image I'd like to think about, where points on the real line get mapped to the red circle, but points in the upper half plane, like these black semicircles that we've been playing with, get mapped to parts of circular arcs. Each one is just part of a circle. They look a bit wonky, don't they? But within the unit circle. That's what I'd like to consider, I think. And I don't think it matters that that point is not at the midpoint of that arc. The midpoint of that arc is something horrible, like 1/√2, minus 1/√2 in coordinates. It's not a nice place to be. Whereas I am sending everything to Gaussian rationals, something like that. Yeah. Right, good art. I kind of want Mean Machine Rex can redeem a Victoria sponge. Yeah, we should have extra. I'd like this idea of extra perks that you can redeem that give me extra stuff based on channel points. Although it does exacerbate the kind of Tamagotchi feeling that we have going on, where you've reminded me that I should go and make a cup of tea. So now streaming is weird. I'll go and make a cup of tea. Beep boop. Right, okay, I will see you in a couple of minutes, as long as it takes my kettle to run, when maybe we'll draw some more circles, semicircles in here. Maybe I'll get happier about the kind of transformations on the reels that we're doing. Might think about doing a kind of translation in here to see what that does. Oh, slider, please. Slider. Might think about doing a transformation, like some sort of translation of the thing in the real line to see what that does to the image in the upper half plane model. For me, it's quite deformed. It's never quite at the geometric midpoint, except there. I'm never quite at the geometric midpoint I'm drawing in, my median point, but I think that's going to be okay. And the idea is going to be some sort of composition to start from that green triangle, find the black triangle, do whatever sensible transformation on the real line you want to do, and then image back again to find out where it's gone as a symmetry of the circular fairy diagram. Back in 2 minutes. If you see an ad, you are at least a tiny bit supporting charity in theory, because it's a not-for-profit Twitch stream. Right, good. Here we go. Tea. It's your invitation to make some tea as well. Ooh, Herb's got special tetrahedron tea bags. I have seen some of those before in my life, but not recently. Ooh, have fun. Right. That one, and then that one, and then that one. Ooh, we're back. Oh no. Missed all the ads because went downstairs for hot water. Good call, Right. Don't listen to me, Twitch. I'm sure everybody watches all the ads and buys everything in them. You should keep doing this. We are back, I think. Right. Here we go. Yes, got tea. My new plan, I think, is to go back into the book. Got some idea about what's going on here. Ooh, it's like a sort of, I don't know, ghost shape. I don't know. Ooh, good fun. My plan is to go back into the book and just kind of slightly arrogantly assume that we've got the kind of core idea that the transformations on the reals give you transformations of the circle model. They send edges to edges. They do everything correctly, and that morally, the thing is just transformations that preserve the rationals and the edge fact, so they need that determinant. That seems like about it, right? Can there be more stuff going on? Let's find out. Right. Only addiction is coffee. Right. Where are we going? And it is a slight arrogance to say, I feel like we've got the gist of this, having read 2 pages of it and then drawn my own diagrams. But let's find out. Right, so composition. I really do not want to read this because this is just matrix multiplication, right? Surely this is just matrix multiplication. Yes, good. Yeah, okay. So it's the composition. Good, right, okay. The product, brilliant. There are inverses because the two matrices. Okay, good. Right, so this bit. Good, okay. Right, orientations. Transformations either preserve the orientation or they don't. That is a little bit, it's going to be hard to work out which one's which. Let's read it. A triangle in the fairy diagram can be oriented either clockwise or counterclockwise if you count 1, 2, 3 along the corners. Yeah. Now, let's think. So we're talking about transformations of the rationals, but I'm reading that as a kind of proxy for transformations on the real line using a integer coefficient Mobius map. So when I read something like this about it taking triangles, I'm thinking about taking triples of rationals. Because that's what a triangle is for them, really. It's rationals around the perimeter of the circle. So I should read triangle as triple of rationals, and then orientation is going to be some fact about which way around they are. What would I do? Look at the signs differences or something between the rationals? Should be all right. Oh, look, here they are. The transformation takes each triangle to another triangle in a way that either preserves the 2 possible orientations or reverses them. So T might reverse everything or just reverse those ones. That's because the orientation of a line is going to be the same for on both sides of the line. That transformation is the same, right? No. Yeah. Why is that true? Why is it preserving the orientation? Broadly, it has some sort of derivative nearby, which means that it's preserving error. So orientation. Yeah, okay, so the inversion or it isn't. Mumble. It's nice to think of triangles. It's just either preserving orientation of the entire plane or not. Now that I think they're Mobius maps. Okay, good. Right. If the orientation of one triangle is reversed, then the orientations of all triangles are reversed. Because, yeah, I still don't feel like I've got a great answer for why that is. Are we going to prove it? Well, we're just going to say it's something to do with determinant plus or minus 1, which is the least surprising thing that it could have depended on, right? AD minus BC. Translation of the upper half-plane diagram by any number of units left or right preserves orientations of the triangles, while a reflection, reverses orientations. And we know which matrices those are. Good, the sign has geometric interpretation. But this is just, that's the same punchline as the matrix transformation, right? So if you apply this transformation to the real plane, then AD minus BC also tells you about the orientation preserving nature of that transformation. Like if AD minus BC is positive, it tells you it's orientation preserving, and if it's negative, it tells you exactly that it isn't everywhere for linear maps. But somehow that's not quite what we're using, because this is still not quite a vector. It's a rational number that's sometimes wearing a kind of disguise. Having fun. I think the fun is just projective geometry that makes rational numbers written in lowest form have something to do with vectors under some particular identity. That's what we're doing, isn't it? We're just quotienting the quotient R2 by the... Yeah. There's really some projective geometry going on here, isn't there? Anyway, I just did a whole section on stereographic projection. Let's carry on. Here's a proof. What is this? If we multiply one column of the matrix by -1, changes the sign of the determinants. Also check whether it preserves or rotates or reverses. And we're going to do that by doing one triangle at a time, which, fair enough, I guess. From here to here, these two triangles are different, so they lie on opposite sides of the edge, hence have opposite orientations. So if you get one or the other, then it's either... Yeah, okay, order oriented or not. It's a very triangle based argument. Well, I prefer, what would I prefer? Something like, instead of arguing about these real fractions, map these points to places in the complex plane using one of these Mobius maps, which is the same idea just with complex numbers. Map it to the actual plane, and then the orientation is... Yeah, then I've got to argue about, in general, if I'm going to take it to the general Mobius maps, I've got to argue about whether they're orientation preserving or not. Which I think is just going to be like looking at the derivative of the Mobius map. But maybe that is a bit weirder, and maybe I shouldn't say all of that. I should just let it be a crazy fact about fractions. Don't know. How is the Mobius map related to... So the Mobius map itself is related to the kind of linear map on R2 in some way that I've forgotten. The Mobius map is hanging around here, AZ plus B over CZ plus D. Looks like a matrix. What's going on there? Fun stuff. Possibly I should be drawing all of my semicircles by doing Mobius transformations. You know, if this is my true understanding of what's going on, then maybe I should be... I don't know. No, maybe not. Nah. Is this a good way to do it in Desmos? Not sure. Jury is out. Right. Okay. Then am I going to do the other quarters of the plane or whatever? Okay. I don't love this proof because it's very triangle based, but okay. Look at what's going on for the biggest triangle and then everything follows from there. Okay. So when we say a transformation takes a triangle with primes on, we mean that it sends each of the corners to the correct places and preserves the order of those vertices. So we're going to say it preserves this triangle, and we mean corner to corner. Similarly, when we say, end of page, similarly when we say that T takes an edge to an edge, we're going to mean in an orientation preserving way. Fun. Okay, here's some symmetries of the fairy diagrams if you've just joined us. They are all of the format rational number in lowest common form, in lowest common terms, x over y in the rational numbers goes to ax plus by over cx plus dy, which is, since these are whole numbers, and I promise you that a, b, c, and d are all integers, this is also in Q. That gives us all different fractions. We've got this kind of diagram where we lay out the fractions around the unit circle. My preference is to get from the real line to the unit circle by using stereographic projection, which is an example of a Mobius map, which is also what's going on over there, because I want to chain these things together. The book would slightly deform that a little bit, but doesn't matter. Okay. It's not the nicest way of doing it. But if you only care about the property of the sequencing, then you're all fine. Yeah, everything's fine. It gets the points in the right order. Okay, so we've got a map from Q to Q, given by this. You have to remember that x over y was supposed to be in lowest terms. I suppose you do get something in lowest terms, provided that AD minus BC is plus or minus 1. And we're very interested in numbers like this, A, B, C, D, where the determinant of that matrix is plus or minus 1. We've had them turn up in quite a lot of contexts in this book so far. They're matrices from a very particular subgroup of invertible matrices. Right. I've decided to just go really fast. Let's find out. I know it says chill maths. I'm trying to be chill, but also I want to get to the point. What have we done? About 5 pages? Hour and a half? Let's get somewhere. Let's go. Are we chill? We're still chill. Good. Okay. Good vibe check from Murray. Thank you. Ice Cube. Nice. Good. We've got tea. It's going fine. Right. So now they're going to tell me for any 2 triangles, this is where the Mobius maps go into play. I think. Hot ice chill. Just water. We've got. Ooh, what have you made? Have you updated the Desmos? Which one's this? Updated the Desmos. Oh yeah, you've got some under projection. There you go. You've projected loads of them. Oh, is it the ones from before? So previously on the show, we came up with a way to draw lots of semicircles in the upper half plane, and then you've mapped them all into here. I think. Well, lots of them anyway. They're getting smaller towards the kind of point at infinity. Nice. Okay. I think the Mobius map is going to help me now because it says any 2 triangles in the fairy diagram. There is a unique transformation that takes one to the other. That is just a fact that I know about Mobius transformations, that they are sharply, triply transitive for any 3 points. There's a Mobius map that takes those 3 points to these 3 points. You can specify the images of 3 points, and you get a unique Mobius map. Reminded you don't repeat yourself. Okay. But this proof is going to not use Mobius maps. This proof is going to use rational numbers only. So off we go. So what I would do is I'd say, so for me the triangle is in the complex plane. So fine, maybe you give me a triangle specified by some rational numbers. I find those points in the complex plane, and then I say your target points. Well, I find those in the complex plane as well, and I find the Mobius map that takes us from one to the other. That transformation. If I stack it together with stereographic projection in both directions, gives me something like a map from the rationals up to my circle, whoop, change which bit of the circle we're talking about, and then back again. I will end up with the composition that is a new complicated Mobius map, but it's going to have real coefficients because it's sending reals to reals at the end of the day. And because it's sending rationals to rationals, I reckon it's going to do this with integers. That's something I'm a little hazy on, but possibly that's not obvious. Possibly not obvious that I land on one of these. Well, you told me you were going to send rationals to rationals. What do I think the coefficients are going to be? Yeah, that's not obvious at all, is it? If you put 3 rational numbers in and get 3 rational numbers out, that A, B, C, and D can all be chosen to be integers. Huh. Depends what I'm going to do in the circle, doesn't it? Depends a lot what I'm going to do in the circle. No, if I promise to end up at a rational point at the end of the day, then I really just need this property that a map of the form. So I'm pretty sure that a map of the form like this, that sends 3 real points to 3 real points, has real coefficients, or could be chosen to have real coefficients. You can divide top and bottom by I or something, and haha, real coefficients. What I actually need is for it to do that on rationals, which is less obvious. So exercise f sends z to this number, if f of p1, f of p2, f of p3 all rational, with p1, 2, 3 all rational as well, then can choose A, B, C, D to lie in Z. Not obvious. Ooh, yours had a slider. I missed that. Sorry. Okay. In a moment, I'm on a roll, I think, with understanding transformations. It's the same sort of punchline I've seen for Mobius transformations. Let's read it. Given pair of energies. Do a transformation that takes. Oh, use that matrix. Clever. So that it's look, they're going to do 1, 0, 0, 1. But they're also transforming. Yeah, they're also transforming back. They're taking these transformations from some sort of basic state into these two positions, which makes me feel like they're doing kind of like, oh, actually invert that, do some stuff over here, and then send it back again. This composition does this. So you've got that takes an edge to an edge, and then either the correct one or the wrong one. Check the orientation. It's clever. Okay. Changing the signs of one column of the matrix T1 or T2, which just means flipping around the direction or something. Flipping the signs. Oh, it still takes you to PQ, but minus P over minus Q or something, but gives you the other orientation. Fair enough. Okay. It's unique since it must take the 3 triangles sharing an edge. So it's going to be a very triangle-based proof again. Okay. The 3 triangles sharing the corresponding edges, and this determines when the next layer of 6 triangles, and so on until all triangles are accounted for. Yeah, fair enough. If you only care about where the triangles go, then doing it kind of inductively every time on your triangles is fair enough. I just don't feel like it's. If I don't believe in the triangles, then it feels like it's still true that 3 points get sent to 3 points, whether or not I'm kind of trying to build, all of space out of some triangulation, but a bit at a time, I suppose. Yeah, how do you know the triangles fill space, or fill any space that fill some subspace that you're interested in? Oh well, never mind. How do you know that that's good enough, right? Is that the target? Is that all we wanted, to do all the triangles, or do we think all of the triangles fill everything? Who knows? Okay, we'll look at fastest version. Wait, is this going to wrap it up? No. Oh, you did make it wrap it up. Oh, it's mad though. Oh, that's really weird. Is that just interpolating between where it started and where it's going? Oh, that's what Mean Machine Rex wanted, I think. A thing that wraps up the real lines. We have all our fairy circles from before. This is really good. And sends them, oh my goodness, wraps them up onto the unit circle. Oh, yikes. Oh, crikey, whoops. Whoops. One more. Yeah, I don't think my computer can render this very fast while also streaming to Twitch. Your mileage may vary at home. Good. Right, close some tabs. Interpolation is cool. Right. Notice how even close to time 1, lots of points are still miles away from where they're supposed to be because they're so very far away. They've got a long way to go. And doing 99.9% of the distance they're still not there. Very far away. So even when it was close to being rolled up, there were bits where up to infinity rolled up, but not there. Good. Okay. Maybe not what you would guess. It does say unstable, which is why I've started closing things and panicking. The panicking doesn't help, but you know, it's kind of the opposite of chill. Panicked Maths, an alternative live stream brought to you by James's overloaded computer and overloaded James. Right. Let's find out what a pivoting transformation is. It's not crashing. It's not crashing. It's just diverting a lot of processor power to another Google Chrome tab. I've got too many Chrome tabs open, I guess, is the real punchline here. Why don't I use some of my graphics card for that instead? I don't know how people do sort of an entire video game at the same time. I've heard that you get a second computer and you do some sort of local broadcast from your gaming computer that's good at games and stuff onto your streaming computer that is sort of physically nearby and doesn't have to talk to it over the internet, and then that one talks to the internet. Goodness me, right. Would truly take a Desmos chart for the ages, I think, to necessitate a new computer just for rendering it separate from the stream machine. Right, good. Yeah. It's quite good of Desmos, really, that Desmos will let you make things that it can't necessarily render. It does. People do like finding ways that Desmos doesn't quite render things right. Like if you just get to draw way too many lines that are way too close to each other. It has issues for obvious reasons, I think. Anyway, remainder of this section, 5 fairly simple types of symmetries to the fairy diagram given by elements. Okay, 2 more in the next section. Ooh, and a connection to continued fractions, so that's good. Okay, symmetries, here we go. Reflection, that does not sound exciting. Other triangles set. Simplest case of reflection there. Reflected across any of its edges, they mean the curved circular edges. So fix an edge and flip everything else by sending the median to the other one. Same reflection across here. Matrix A, B. Oh, that's clever. That's clever. Oh, and then do so. This combination of transformations, by the way, you see quite a lot in maths, right? This says you currently have something complicated. The inverse transformation here is to bring it back to somewhere simple. You say your complicated edge was related to your simple edge by some sort of transformation. Like it's gone over there. Why has it gone over there? So the story is always bring it back to the simple place. Do something obvious when you've got it in the simple place. So do the transformation t, which here is just negative numbers, and then do the transformation s to go and put it back where it was. In this case, we want to put it back because we're trying to flip everything relative to that line. So we take the line, we move it to where we can see it, flip everything. Well, okay, flips everything on each side, but keeps the line, keeps the endpoints in the same places. So now we're free to move it back again and see what's happened. And I've seen this story quite a lot. It's the change of basis formula as well. If you do linear algebra, which are we doing linear algebra now? Discuss. Anyway, here's the description in words. Which, once again, I've read out a sentence. I should just read on, shouldn't I? That's a good diagram. Okay. Here's a matrix for it. Ooh, that's not too bad. Yeah, so here you go. There's the flip. Here's the transformation back. It's putting it back where he started. Nice. Okay. What does that do for us? This is going to turn out to be something like writing the continued fraction backwards or something, because we know the continued fraction is related to the sequence of triangles that you get. If you're homing in or a point over here, you do this by counting how many times you sort of go left and right through the diagram to get to a point up there. So then flipping it upside down, inverting it, is going to be, and then reading in on whatever point you get in there, it's going to be a bit like reading the continued fraction backwards. Maybe you get the same number, maybe you get a combination of a new number or something if you write the continued fraction backwards. The diagram can also be reflected across an arc perpendicular to any of its edges. Ooh, dotted arcs. Very nice. So this is going to be, bring the line where you can see it. I'm not reading. Bring the line where you can see it. Exchange the endpoints, send it back. Possibly flip up and down as well. And the matrix in the middle is going to have ones on the off diagonal and zeros here. Maybe a -1. It depends if you want to see the reflection at the same time or not. Right, okay, let's read on. Down here or something. Reflection, what's t? The vertical X is this one, which does the inversion. Yes, good, good, good. Not hard to commute this. Leave it as an exercise. Haha. Okay. Now, I thought I was leaving it as an exercise for the book, but then it left it as an exercise for me. Okay, you can rotate 180 degrees. Again, we've got a basic one in it. Right, okay, I see the pattern now. It's just going to do this every time. It's describing kind of things that are obvious on the biggest triangles. Right, so then you've got 120 degrees. So this, about the center point of any triangle. They don't really mean degrees, because where's the center, right? I mean, any triangle you can find a point where... Can you do this? Yeah, you can definitely do this. You can find a point where the angles work out. I can't remember which center that is, don't test me. So they're going to talk about doing this to the basic, a really big triangle to interchange the corners. And they've got a matrix for doing that. Well, they've got a transformation for doing that. So to cycle around these corners, they're saying go to y over y minus x with this matrix over here. Because that moves the edges around correctly. And then it's going to send the other corner around correctly because it still involves the same sorts of corners, right? So if you know 1 over 0 goes to 0 over 1, and you know 0 over 1 goes to 1, 1, then the sensible question is, where's 1, 1 gone? Not obvious. I think you can read it off here. It's gone to 1. Has it stayed still? No. I want to say it's gone to 1 over 0. Not obvious from this, because you could have done this wrong at this point if you're just mapping the edge around. There's lots of maps that take an edge to an edge. You need to get the other corner right as well. Yeah, fine, okay, just do this map because it sets the corners to the right places. Okay, you've got rotations for triangles. So they're going to be some sort of... Right, what's this pivot then? Pivot. What does this mean? Okay, here's SDS. Inverse. If the vertices joined to V by edges are labelled VI for all integers I, with VI joined to VI plus 1 by an edge. Mean Machine Rex has got T! Hooray! Oh, good. I love an Earl Grey. I'm on standard Yorkshire tea at the moment, which is excellent. Not sponsored, but if they're watching this, then wow. Why haven't you got in touch already? You already found the stream, Yorkshire tea. Why are you waiting for me to tell you that I would love a sponsorship? I love the idea that... never mind. Sorry, I've been really taken by an idea that I just... Anyway. G'day. Oh, hold on. Earl Grey. Great. Pivoting transformation. What is this pivoting transformation going to do? Show is not very clippable, is it? Because you try and take a clip of some like good maths moment, and it has in the middle of it a sidetrack about T and a sort of meta bit like this, where I talk to the camera, and then I get back to finishing the sentence. This point goes to the next triangle. Next triangle. What order did you number them in? Oh, the numbers, they're joined to each other as well. My goodness. That's a bit of a mess. What's going on then? So this is the observation that they're joined. You look at the triangles coming out. We see these points on the upper half plane model. We see these points with lots of lines coming out. And you go, right, it's coming to loads of other points. It's positive and negative, maybe. Because we see they're going on both sides, infinite in both directions. There's like lines springing out. Oh, I should use all my fingers. There we go. Woo! From a single point. And the idea is to just move one along. Powers, and I guess including powers of the inverse. Also pivoting transformations, sending this to that. Yeah, positive or negative identity or inverses will be necessary, right? So horizontal means pivoting about the vertex 1, 0, because 1, 0 is right up at infinity and connected to all the integers. So then shifting along by an integer just changes which integer you're joined to. Fine, okay. N steps clockwise. Let's just do that one and then transform it forwards and backwards. Yes, off we go. And that is a matrix that we've seen before. Or is it the transpose of a matrix we've seen before? It's not quite a matrix we've seen before. It's one of my sheer ones, isn't it? Good times. Penn Centre's here. Hello, Penn Centre. Good to see you. We are reading Hatcher's Topology of Numbers, but I'm arguing with it about topology, or in the sense that I don't think we've done any topology yet, but the book and I have got different preferences for how to set up a very particular map, which I've been telling Chat about, which is maybe irresponsible of me. I should be just letting Chat read the book. I'm doing my best to learn number theory again. And I think, look, I've been good, right? I've done 6 streams in a row. Is it 6? Maybe 5 or 6. 5 or 6 streams in a row on the same book. Just trying to get through. We don't read notebooks. Right, okay, look. You know, I'm supposed to be modelling, I'm modelling behaviour, right? You could read a book too. 5 or 6 streams on the same stuff. I used to be described as a variety streamer. I've cut that out. One person described me as a variety streamer one time. Bless them, I think they were wrong. Right. Just maths. Exactly, Penn Centre. Exactly. Are they Mobius maps? Are they, though? The book is only interested in ones with real numbers in, and I think it's only interested in ones with integers in, because for the book we are only transforming the rational numbers Q, and it is frustrating to me that I think you can just extend everything to C and nothing goes wrong, but we're particularly interested in rationals for this book because we're doing number theory about primes and stuff. Hello Meglamorph, you alright? Were you here before? Oh yes, you said something about T earlier. Sorry I missed you come in. Right, good. Okay, in particular, the particular semicircles we've got in the upper half plane, which we have the upper half plane even though we don't really have C. We sort of have C, I'm being mean. If I ever seem adversarial, it's because learning maths is hard, not because of deficiencies in the book. Right. Yeah. We're sort of shearing, aren't we? I know this transformation. Is it relevant that we know this? Because we're secretly doing this to the vector PQ, which we will sometimes interpret as being a bit like the fraction P over Q. But the problem being that the point PQ in space is kind of almost nothing to do with the value of P over Q, unless you do some projection, right? Or you've got to map it down somehow to think like, oh dear. Wait, is that what I'm supposed to be doing? Oh, that's nuts. If that's just what we're doing. Am I just supposed to project points from z squared onto the unit circle and call it a day? Yeah, maybe I am. Maybe I am. Oh dear. Maybe you're just supposed to read around looking at all of the points. Yeah, P and Q are supposed to be in lowest term. No highest common factor for us, please. Right. Yeah, we've only got one infinity. Good, right, I'm catching Penn Centre up on a book. Oh, the book, by the way, is freely available. And is Hatcher's Topology of Numbers, which you can get at pi.math.cornell.edu/tilde-hatcher. And they have other books as well. But this is the only one I stand a chance of understanding. So there we are. Oh, right, we've hit some exercises. Fun. We've got some symmetries. The symmetries are, I still think, just Mobius maps of the unit circle, where I have a kind of, I guess, personal sort of conjecture, I suppose, that if Mobius maps send enough rational points to rational points, then all the coefficients are nice. So we've captured all of this theory just by saying Mobius map. I haven't proved that, so maybe that should be my exercise. Yeah, so maybe it should be for me. Where did I write it? Down the side, really tiny writing that you can't read. But I have a marginalia kind of conjecture here, and no space to prove it. So that's acceptable behaviour, right, for mathematicians. I'll just put down here. Seems true. Not much space. There we go. Oh dear. No proof for you. Right, megalomorphics can tell me about projective homogeneous coordinates. Yeah. I can't remember what an action of PGL2 means, but I'm pretty sure that is what we're doing. Right. Okay, good. Just feels true. You send enough. If you send 3 rational points to 3 rational points, then you've got a map from reals to reals, I reckon, and from Q to Q. Let's try and prove it a tiny bit. Is that going to be fun? No, it's not going to be fun at all. I think I should. Yeah, I would just. So proof concept, proof idea. Proof idea. So in the language of the conjecture up there, write out your fractions. I regret calling them p, by the way. I'm going to change them to x1 for inputs. Same thing for 2 and 3. Write them like this for your inputs. Solve for a, b, c, and d, because I think Mobius maps are sharply triply transitive, because that's a fact that was drilled into me in first year of university, which was a very long time ago. Solve for this, and then we're good. Do I want to do that? Not entirely, because I think the expressions of A, B, C, and D are going to be not very pleasant. But I think there'll be sort of things which then you point at them and say, well, look, they're all rational, so multiply up by the lowest common multiple of the denominators, and then you've got integer coefficients in your Mobius map. So you send rationals to rationals. Yeah, maybe without loss of generality, D is 1 is probably acceptable. You might not be able to get away with that in general, but it's close enough. Like, what if D is supposed to be 0? Then you shouldn't set it to be 1. So I think we'll put all right. Penn Center, you don't just get shears. There's other transformations that that was kind of case 5 or something that you saw. We've also got things that are a bit like reflections. We've got things that we've got the obvious ones. We've got reflections. We've got some more reflections. We've got some rotations. We're very interested in these lines that connect. Well, in some sense, connect 2 points on the unit circle, but we're labeling them with fractions. So they're sort of connect two fractions. 2 fractions are connected if and only if. So A over B and C over D are connected. If and only if AD minus BC is plus or minus 1, which is sort of a determinant fact, right? And then probably your reaction is something like, those aren't fractions, those are points on the unit circle, where do you put the fractions? And my answer would be just stereographic projection to get them from the real line onto the unit circle. The book does something slightly different, but that's what I would do. Shall I prove they're triply transitive? Well, yeah, it's the same proof, isn't it? I think the proof when I saw it many years ago was something like the same structure as this, but without assuming fractions. Throw in Z1, Z2, Z3, solve for the coefficients, and say, look, I've solved for it. I've got a unique solution. So this is the aim, to get a unique solution to say, give me 3 points and 3 targets. I can find something that does that. Probably, actually, thinking about it, instead of doing any 3 targets, I should do 3 basic points going to my favourite 3 rationals or something, or to any. Yeah. Okay, I've got too much stuff. Where it says not much space, I should be replacing that with stuff. Idea stolen from the notes. is instead of thinking about sending 3 arbitrary points or 3 arbitrary rationals to 3 arbitrary points or 3 arbitrary rationals, I should think about sending 3 basic points like 1, 0, and infinity or something to my favourite 3 rationals or my favourite 3 points. And if I can prove that's a unique transformation with an inverse, then to do an arbitrary transformation, I do the inverse first. You've got 3 weird points. Whoa, let me move those to my favourite 3 and then send them off on their way to their destination to do everything via my favourite 3 numbers. And my favourite 3 numbers, I think, are 0, 1, and infinity. Okay, let's do that. So let's do a map that sends 0 to really no space here. Let's go on the left margin. We had a lot of fun with the left margin earlier. Let's try that out. So we're looking at map of the form z goes to az plus b over cz plus d. And what I want is for 0 to go to my favourite point x1, for 1 to go to my favourite point x2, and for infinity to map to my favourite point x3. I've only got 1 infinity here. -1 better than infinity? Maybe. Maybe better. Infinity's nice because you sort of just do some sort of limit, right? And it's just a over c. Maybe that's a bit cheeky. Maybe people won't like this. Yeah, possibly I'm supposed to put these points on the right hand side actually. The inverse transformation might be easier to think about. Yeah, this is going to be much easier. This feels more like the proof I saw. Because then x1 goes to 0 tells me that I'm supposed to have a multiple of z minus x1 upstairs. x3 goes to infinity, says I'm supposed to have a multiple of z minus x3 downstairs. And then x2 goes to 1 tells me that the coefficient I should write out the front here is x3. So that's a number out the front, which I could imagine multiplying. You know, really I should, to get it in this format, I should tell you that a is this number and b is minus x1 times that number. So it should all go up into the numerator really, but yeah, come on, this does the 3 things that it's supposed to do. Is it unique? Well, I should probably write out some equations for that, right? And it'll only be unique up to multiplying a, b, c, and d by a constant, because multiplying top and bottom of this fraction by a constant is fine. Right, glad I thought of the inverse trick just before. Did I think of it, or did Megalomorph say it in chat? Let's have a look. Yeah, Megalomorph said it in chat. Good thing Megalomorph said that at just the right moment. Good. So that shows that it exists. I'd quite like to show that it's unique. For which... No, it has to be this, doesn't it? I did it out loud without writing stuff down, but I think it has to be this. Well done, Megalomorph. Yeah, the equations work out really nicely. So you could convert these into equations for relating together a, b, c, and d, but they're really nice. Like this first one just says that b is minus a. This one really does say that d is minus c, and then you're in this situation where up to a constant, you only care about this thing up the front. Okay, so I think that shows the Shockley triply transitive. I've been in that sort of seminar where the audience are more involved than is perhaps average. One seminar speaker, we had referred to this experience where multiple audience members were sort of heckling, but sort of heckling each other. There was some sort of like disagreement. There was kind of like nested levels of heckling. The speaker said, I love speaking here because sometimes it's like going into a shark tank and sometimes the sharks eat each other, which seems quite a lot of bravado in the moment. Anyway, terrifying seminars aside, with or without the Megalomorph, I think so. Did it too fast to prove that it was unique, but good. Right. Okay. So then, if rational Well, I think it's kind of obvious then that if by all I mean x1, x2, x3, if they're all rational, then I think it's kind of obvious that these numbers are all rational. I guess some subtraction and division, but come on, that's a rational number. So then you've got rational coefficients. So particularly you've got real coefficients, but better than that, you can multiply up LCM, the LCM of the denominators. Excuse me, to get integer coefficients. I'm not quite done because what I'd like to say. Yeah, these maps will send any three rationals. I can use these maps for sending any three rationals to any three irrationals. Hooray, brilliant. But, ideally, I'd just be looking at the ones that do... Yeah, okay, so then the refinement is that if you want to preserve whether or not those 3 points were a triangle in the Fairy diagram, you need to make sure that you have AD minus BC as one apparently. Meglemorph got timed out. What did you say? Meglemorph, sorry. Why did it delete your chat history as well? No. Did you hit one of our ban words? No. We got a false positive. You're back. Good. Right. You've discovered a word that we're not allowed to say in chat. Mary, don't make me ban it without the space as well. We used to get robots. I hope you're all right, Meglemorph. Hope you survived your 1 second ban. 1 second ban's enough for robots. Don't make me. You said something different. What if I called my ban list? Did you do an actual swear? He says in horror. Right, good, okay. No, I'm interested. It's about 4 o'clock, so I'm sort of supposed to be wrapping up. Let's have a look. I'm gonna put the thing with as a workaround. Word protection. Let's see. What have I got? Really, only got one. Oh yeah, you get a purge. Sorry, all of your insightful, great comments from just moments before. Yeah, I think Streamlabs might have been a bit overzealous there. No, I can't see what you've written, or indeed any of your previous messages. I don't think I can. Or maybe I can find out. No? Oh, this is a good Twitch exercise. I'm not going to do any more maths, I think. I'm just going to learn how Twitch works. Great, right. You seem to have survived the experience. Yeah, moderators just deleted that. Machine Rex might have seen it for 1 second. Right, good. Okay, Twitch. Okay, we've got some symmetries. Let's wrap up then. We've got some symmetries. I think they're just Mobius maps. I'm pretty sure that if you send rationals to rationals, then you're all good. But it's the ones that preserve, the ones with determinant plus or minus 1 that are particularly interesting to us because they send edges to edges, wedges to wedges. Next up, translations and glide reflections. That's a nice category of reflections. Where have we got to then in the grand scheme of things? We're about 8 pages further than we were because I think that said 70 at the start of the stream. So 4 pages an hour. And I've discovered another textbook I'm interested in where 250 hours of content. Oh dear. I think I might be wrapping up. I said I would. I think we're going to be okay. Does this really say find all the transformations that fix? So these exercises, one of them says find all the ones that fix 0, 1. And then this one says find all the ones that fix 1, 1. Those are related concepts, right? So I want to fix 1, 1. I can move it to 0, 1. do a transformation that fixes 0, 1, and then send it back to 1, 1. And that will parameterize all of the ones. So if I've done part B, then I think I can just do part E by doing kind of STS inverse thing, which is the matrixy kind of thing that we do around here. A textbook. The textbook that I found that I'm interested in is, you might have heard of it before, is called Napkin by Evan Chen. I've heard the name Evan Chen before. They, I think, are something to do with Olympiads. They have written, whoa, crikey, I clicked an ad. They have written, whoops, they have written 1,000 pages of trying to explain hard maths to people, which I'm quite distracted by because it contains such exciting things as differential geometry. And it does linear algebra properly, which is a good, I think, a good ad. Right. You can also do complex analysis and quantum mechanics in this book. Although the quantum mechanics is quite a sort of selective subset of all the quantum mechanics that you can do with maths. Maybe this is under the guise of doing it properly. Here's the map of everything in this. You know, it's quite exciting, and there's 1,000 pages. So once we've finished Hatch's topology, that's 1,000 more pages of stuff. Yes, right, okay. He's the one. Right, that's where I've heard his name before. Sometimes I tell people I stream on Twitch, and they say, "Oh, have you heard of Evan Chen? He streams on Twitch. He solves Olympiad problems." And I think, right, that sounds terrifying. Well, chill maths. Not very good. Very good. Right, there's the Twitch plug. Thank you, Megalomorph. Don't forget to subscribe to Venhance for Olympiad maths, and also follow other people in this Twitch thread. Some of them are also streamers. They might plug their own channels if I hang around for another minute or two. We're going to come back, I think, next week to think more about... Are we back next week? Probably back next week. Back next week to think more about symmetries of the Vary diagram, which I'm still going to understand to be Mobius transformations, especially now I've convinced myself that the ones that preserve rationals are the ones with integer coefficients, more or less. You're not a problem. This is the content. You made affiliate 4 years ago tomorrow. Congratulations, Megalomorph. There you go. Told you it would happen. You can maybe find, I don't know, former content or something. Who knows? Right, good. Okay, next time we're going to get a connection to continued fractions, because I can see one of our continued fractions in this diagram below. Possibly these symmetries will relate to properties of continued fractions, and this story might be leading us to understand why continued fractions for square roots of numbers have, I don't know, periodic continued fractions that look the same forwards and backwards. Kind of symmetries in the sequence of numbers related to symmetries in the sequence of triangles that you get. Because key idea in this book is that the numbers in the continued fraction relate to triangles in the Vary diagram. Good, right. I will see you next week. In the meantime, have a nice weekend. Have a nice week. Good luck with all of your maths. Yes, goodbye. I'm stopping the stream. Bye, everyone. I have a sign off that Herb wrote for me, which is, I'm stopping the stream now.